And here we go again. So I'd like to expand on something we touched on the other day. I'd like to talk about how to solve problems where there is something rotating. And what we did the other day is we had an Atwood's machine, and then we made the pulley on the Atwood's machine be heavy. So let's put together an Atwood's machine here. Two different size and shape objects. Let's have this one be 5 kilograms and this one be 3 kilograms. And for this example, we're going to do it in the old-fashioned way, where the pulley is going to assume to be massless and free of friction. So there's going to be some tension, and we have to solve this by generating a couple of free body diagrams. I know there's a system trick, but let's do this by generating a couple of free body diagrams. Okay, so we're going to have mass 1, mass 2. Mass 1 times G pulling down this way, and the tension pulling upwards. And then mass 2 times G pulling down this way, and the same tension pulling upwards. Now, I suppose we could call these two different tensions and prove that they're the same. But in the case of a massless pulley, we've done that work before. We've showed that. So you're going to generate two equations. One is F net equals m times A for this mass, and the other is F net equals m times A for this mass. Now, consistent direction. This thing is going to go this way, so I'm going to call downwards motion of mass 1 positive, upwards motion of mass 2 is positive, and counterclockwise motion of the pulley is positive. So let's go ahead and put this in here. We're going to have m1g minus t equals m1a, and then this one is going to generate us t minus m2g equals m2a. Remember, this is for this mass, so the mass that you put in this thing is mass number 2. And this diagram is for that mass, so you put in mass number 1. Now we have a system of two equations, and my two unknowns are the tension and the acceleration. And general rule of thumb is solve for the one that you really don't want. And substitute that in to the other equation to get the thing you're looking for. We're going to need to distribute again and collect terms. So this m2 times a, which is minus, is going to come to the other side. We're going to wind up with m1g minus m2g equals, and then we're going to have m1 plus m2 times a. And we get the result that we had before, which is that m1 minus m2 times g, all divided by m1 plus m2 equals the acceleration. That's the acceleration of an Atwood's machine. And this is what led us to the system trick, because we noticed that the sum of the masses was here, and we wondered if we could just treat this thing as if it was one mass, one thing, being pulled to the right with m2g and being pulled to the left with m1g. Could we then quickly get to the acceleration? And we could, because we would have, this being the positive direction here, we would have m1 minus m2 times g for the net force, and m1 plus m2 as the total mass. And we would get this result very quickly with just a little imagination. We may try to do this with the heavy pulley Atwood's machine, but I'm not sure. All right, let's do this with a heavy pulley now. Our pulley is going to be assumed to be a disc of some type, so let's go ahead and draw the picture. And now we're going to have a disc of mass m, d, and radius r, and then hanging from that is going to be our same mass 1 and our same mass 2. Again with the 5 kilograms and the 3 kilograms. I didn't really use these last time, and I didn't use them last time. I only used them to establish which way the system would move. All right, and so I could continue here with this. Let's make this be 1 kilogram of pulley. Okay. All right, so now we're going to have a T1 and a T2. These are definitely going to be different tensions because there is something in the middle here that's providing some more inertia, the rotational inertia of the disc, the pulley. So you're going to have to pull extra hard on T1 to get the pulley moving, and the remaining force will be transferred over to T2. This is going to have a different, I would say, smaller acceleration. Okay, now we need to draw 3 drawings. We need to draw M1G and T1 for mass 1. We need to draw M2G and T2 for mass 2, and we need to draw the pulley with 2 tensions, T1 and T2, providing some torque on it. This is an extended body diagram. You have to show the extended body because we need to know how far away from the pivot point each of these forces is acting so we can calculate the correct amount of torque. Oh, and by the way, this thing is going to move this way, so all positive directions are for that sense of motion. So this is going to be an F net equals m times a moment. This is going to be an F net equals m times a moment, and this is going to be a torque net equals I times alpha moments. Now we're going to generate a system of 3 equations. Here we have M1G minus T1 equals M1A. This one is going to be T2 minus M2G equals M2A. And over here, let's see, we're going to have a torque that is T1 times R, and then a negative torque that is T2 times R. That's turning it the opposite direction. And that's going to be I times alpha. Now we need to work on this one a little bit because these are angular variables and these are all linear variables. So I would like to get all the angular variables out of here and replace them with their linear counterparts. And to do that, I'm going to remind you that alpha is the same as A over R. That's true as long as the rope is not slipping on the pulley. I'd also like to remind you that the moment of inertia for a disc is 1/2 mass of the disc radius squared. All right, so if I put those things in here, we're going to wind up with T1 minus T2 times R. I'm just gathering the R's. Then we're going to have 1/2 mass of the disc, R squared, and then we're going to have A over R. And this is kind of interesting. You see, the R down here cancels the square, and then there's an R on each side, and they cancel as well, leaving us with T1 minus T2 equaling 1/2 mass of the disc times A. That's kind of convenient. Let's see what else we can do with this. Well, we have 2 more equations here. Since we're trying to get rid of the T's and we're trying to get A's, let's solve both of these for the T's. T2 equals M2 times A plus G. And over here, T1 comes to that side, this comes to this side. T1 equals M1 times G minus A. I think I got that right. Now we can put these expressions right into here. So T1 is M1 times G minus A. T2 is M2 times A plus G, and that's going to equal 1/2 mass of the disk times A. All right, we need to collect all of our terms that have A onto one side. I'm going to run out of space here, and I'll put the answer over here in this corner. I know it's a little counterintuitive, but there we go. So we have an M1 times minus A, and that's going to go to the other side. And we have a minus M2 times A, and that's going to go to the other side. So they're going to go over as positive numbers, leaving behind M1G minus M2G. And on this side, we're going to have A times 1/2 the mass of the disk plus M1 plus M2. And so when all is said and done, coming over here now, A is going to be M1 minus M2 times G, and then divided by the sum of the masses, but an extra term in the inertia down here, an extra term that is 1/2 the mass of the disk. Now, why is that 1/2 in there? That 1/2 came from the original recipe for the moment of inertia. So if you wanted to pull off a system trick, and again, if you do this on the AP test, you better tell the grader what you're doing because it is not considered not everybody signs up for this method, but if you were to do the system trick, you would have mass M1 connected to a pulley connected to mass M2, and it would have a force M1G pulling this way, a force M2G pulling this way. Same forces, but now the inertial term is the sum of the masses plus the moment of inertia divided by radius squared. This moment of inertia divided by radius squared is an unofficial, but absolutely correct way to include the inertia of the pulley in this thing. Okay, I have another example to do for you, but I'll do it in another video. So let's get this one uploading as quick as possible.